So in this video, we're going to dig a little bit deeper in interpretation of the differential. And I think it's probably best through an example. So let's consider the function y is equal to negative x squared plus 6x. So we know that, so if we let y be our, so we're going to let f of x represent y. We've already discussed that the differential of y is equal to f prime of x dx. So first off, we'd have to calculate this function, and it's going to have two variables, the x and the dx. And as we've talked before, that dy, as long as dx is small, dy is a good approximation of the change in y. And this is really what I want to expand upon in this video. So let's go through the first process of figuring out what f prime of x is. Right, so as we've done in the previous problems, we will first compute delta y here, and then compute the standard part. So delta y is f of x plus delta x minus f of x. Hopefully this is getting old for many of you, and we will speed this process up, but it is important that you understand this process here of computing the differentials directly from definition. So this is equal to negative x plus delta x squared plus 6 times x plus delta x minus, I'll use the whole bracket, minus x squared plus 6x. Running through the algebra here, I get a negative x squared plus 2x delta x plus delta x squared plus 6x plus 6 delta x. Then this minus distributes through, so I get plus x squared minus 6x. And I can clean up already because there is a 6x here and a minus 6x there. All right, distributing this negative through, we get that this is equal to, let's see, negative x squared minus 2x delta x minus delta x squared. What's left over here is a plus 6 delta x plus x squared. And again, everything without delta x's should cancel. So we get, here's a minus x squared, positive x squared. Everything else has delta x's in it. And I'm just, for ease of notation in a second, I'm going to factor that out. So this is going to be minus 2x. I'll put this over here, plus 6 minus delta x, and I factored out a delta x, because I know in the next step I'm going to want to cancel. Great. So there's our delta y. So our f prime, our derivative, is the standard part of delta y over delta x, which is equal to the standard part of negative 2x plus 6 minus delta x times delta x divided by delta x. And as I foreshadowed, the delta x's cancel. And so now I'm taking just the standard part of negative 2x, which since x is real is negative 2x. the standard part of 6, which is 6, and then the standard part of an infinitesimal, which is 0. So this is equal to negative 2x plus 6. Great. That's the derivative. Then what's the differential? Well, let's go back up. And the differential is just f prime multiplied by another symbol, the differential of x. So dy is equal to negative 2x plus 6 dx. And I want to point out that we've got two variables here. Right? So the differential of y, this is a dependent variable. It is dependent on the value of x. It's also dependent on the value of dx. So I could have written this using function notation, saying that dy, it has two free variables, x and delta x, or dx, and it equals, well, the same thing, negative 2x plus 6 dx. So it's important to recognize we've got two free variables. So when we want to do applications with the differential, we want to use it for something, recognize we're going to have two inputs for the problem. So let's look at an example. Say use the differential to approximate delta y, change in y, when, say, x is equal to 2 and delta x is equal to 0.5. So I've got my differential, it's up here. So I'm just going to evaluate. This is all this is asking. Say, okay, x is equal to 2, so we're going to put a 2 in for x. And delta x is equal to 0.5. Well, when we do these applications, the differential is identified as the change in x. So they're one and the same, and this will be 0.5. Okay, so in this case, the differential of y is equal to negative 2 times 2 plus 6, then dx is going to be times 0.5, which is negative 4 plus 6 is 2, so that's 2 times 1/2, which is 1. So using the differential, the change in y is approximately 1 unit. Now, let's look graphically what that is implying. Because remember, the differential of y, which I talked about earlier, the differential of y is exactly what we get when we use the tangent line to approximate the change in y. So let's come over here to Desmos. I have this already graphed. So this red curve is our line, or curve, sorry, negative x squared plus 6x. The green line is our tangent line at the point when x equals 2. So we were looking at when x equals 2, looking at the approximation. So now I don't have delta x being 0.5 yet. So let's slide this over. If I'm changing x by 0.5, then x value should be 2.5, which is right there. All right, so we've changed our x value by 1/2. So instead of 2, we're at 2.5. And the true y value would be 8.75. And the true change in y would be 0.75. But if we were to use the differential to approximate it, again, the differential is measuring how much the tangent line changes. So here's the same, when x is 2.5, then on the tangent line, the y value is 9. And so the change in the differential, or sorry, not the change in differential, the differential itself is 1. And we can see that it's not a great approximation. It's okay, depends on what you want to do with it. But we've got an error with our approximation by about a quarter. So depends on if you're trying to just use this to approximate some function for something local, like I don't know, shooting a basketball into a hoop, or if you're trying to use this approximation to land a spacecraft on Mars. So locally, shooting a hoop, if you're off by your estimates are off by 0.25 inches, you're probably fine. Um, Getting a man on Mars, well, if our initial error is off by 0.25 inches, that's going to grow exponentially as we start moving further and further away, and we'll probably miss Mars completely. So application is important, how much the error is, but still we can see here if we use the differential, we're off by about 0.25. Now smaller values, smaller changes in x reduce our error. So let's slide this down and maybe get to, I don't know, let's get to 0.1. There we go. And now we can see the error is only 1/100th. So the error between estimating using the tangent line or the true is not that bad. And let's zoom in. And again, we're still doing the same thing. This error, the differential of y, is measuring up to the tangent line. The true change in y is measuring up to the curve. And at this low of a scale, the estimates, the tangent line and the curve are pretty close. All right, so hopefully that gives you a little bit of some intuition about what these differentials are doing, what they're measuring, and what they're